Hello everyone and welcome to this lecture. Till now we have seen the results on the adjacency matrix of the sign graph. Okay, so in particular we have seen a spectral characterization of balanced sign graph. In this lecture we will talk about the Laplacian matrix of sign graph and also weakly balanced sign graph. Okay, so let us first start with Laplacian matrix of sign graph. Okay, so let us take a sign graph. Suppose we denote it by GS. Let GS be a signed graph. Okay, signed graph. Okay, so what we mean by first of all Laplacian matrix of this? Okay, so it's just like what we do for unsigned case. Okay, so Laplacian matrix is nothing but degree. The degree notion is same. So the number of edges which are incident on a vertex we call its degree. So this is a degree matrix minus the adjacency matrix, but this now is a sign adjacency matrix. So let me denote it by S. Okay, so this is sign adjacency matrix. Okay. Now, if you see it carefully here, so if you do, we have seen that X transpose LX in the unsigned case was nothing but summation over all edges Ij, and then this was the quantity, right? This was the quantity. So we have seen it many times. But in case of the Laplacian matrix of sign graph, what will be this? This will be nothing but, so let me write it. So let me actually denote it by just LS. Okay, for simplicity, LSX is nothing but summation over again all the edges Ij. Okay, and now there will be this, the sign of the edge I and j, the sign of the edge I and j. Okay, so let me write this, I comma j times xj, and then you do square. Okay, so where this is equal to 1 if I and j are positive. So basically let me actually denote this edge by this r by plus equal to minus if this h is with minus sign. Okay, very simple. Okay, now the first result that we will prove is can be just by looking at the eigenvalues of the Laplacian matrix of sign graph can be determined whether it is balanced or unbalanced. Okay, so let us prove it. Okay, so let us prove it. First let us actually state and then we will prove. The statement is this. Okay, let G be a signed connected graph. Let GS be connected signed graph. Okay, graph, then it is balanced. It is balanced if and only if LS is singular. LS is singular. By the way, let us consider the case, because if you take the unsigned version of a sign graph, this by default is a balance, right? And we know that the Laplacian matrix is always positive semi-definite in that case. Okay, in that case, and the smallest eigenvalue is always 0. So hence it is singular. But we have to also prove here that suppose the for this sign graph, if the graph is unbalanced, then it is not singular. Okay, it's non-singular. Okay, so let us prove it. Proof. Okay, assume first of all let GS be balanced. Okay, so let GS be a balanced signed graph. Okay, be a balanced signed graph. Very good. Okay, now we know that if GS is balanced, then it can be partitioned into two. Basically the vertex set can be partitioned into basically two vertex subsets. Suppose let me call S1, S2. All the edges are here positive and everything here is negative. Okay, everything here is negative. Okay, so now let us write that. So basically if you try to write down the Laplacian matrix of this, what will be it? The Laplacian matrix, so let me write down denoted by LS, it is nothing but this. Okay, so there will be suppose some part A, I am actually partitioning. So A is corresponding to this S1, then suppose P, this will be P transpose and B. Okay, so B is corresponding to S2, A is corresponding to, okay. Now if you see carefully, B has entries what? They have sorry, no, not B. P has only 0, 1 entries, right? 0, 1 entry. Okay. Remember the definition of the Laplacian matrix of signed graph. Okay. So whenever so because this P corresponding to the negative edges, but we are actually making here minus of A, right? Sign adjacency matrix, right? Sign adjacency matrix. Okay. So this will be, in fact, this will be plus, right? It will be plus. Okay. But if you talk about, this is about GS. Okay. If you draw the underlying adjacency matrix, if you draw the underlying adjacency matrix, this matrix is nothing but that. Then L will be nothing but A, then minus P. Okay, wherever there are plus 1 here, it will be minus 1. We have seen it, right? The off diagonal entries are 0 or minus 1. Okay, depending upon whether the I and J vertex has an edge or not. So this is minus P transpose A. Now we will prove that LS and L have the same eigenvalues. Okay, so it is very easy to prove. Actually, we have already seen in when we were doing this spectral characterization in terms of adjacency matrix. Okay, so suppose LS x is equal to lambda x. Okay, in fact, let me actually write this x in actually basically partition form, some partition form. Suppose this is x, y is eigenvector corresponding to lambda. Okay, then what will happen? If you see carefully here, we have to multiply this. So this is nothing but ax plus py equal to lambda x. Okay, then p transpose x, yes, correct, plus by equal to lambda y. Okay, now if you see carefully, using this we can actually conclude this. Okay, so let me minus x. Okay, you see it carefully, then minus py. Okay, this you can actually write as minus x. Okay, just we are rearranging the negative signs here, and then you can actually write it p transpose minus, then minus x. Okay, and then plus this dy, you will getting this. This means that, this further implies that, in fact, this says that A minus p transpose B times minus xy is nothing but lambda times minus xy. That means what? Lambda is also eigenvalue of the unsigned Laplacian matrix. Okay, so that means these eigenvalues are same. Okay, but we know that the lambda n of G is equal to 0. This should be equal to lambda n of GS. Okay, this implies the eigenvalues are same. The eigenvalues are the same, and this implies this. Okay, so in this case your basically the Laplacian matrix of signed graph is actually singular. Now let us take the case when this GS is non-singular. Okay, so suppose GS is sorry, we have to actually prove that. So suppose GS is now is unbalanced. Suppose GS is unbalanced. Okay, that means what? There exists a cycle which is unbalanced, right? So that means, so it implies that there exists a cycle Ck, okay, having an odd number of negative edges, an odd number of negative edges. Okay, odd number of negative edges. Okay, in that case, how can we prove that the Laplacian matrix comes out to be non-singular? Okay, so let us see actually the unit eigenvector corresponding to lambda n. Okay, so let us take lambda n of GS. Okay, and take a unit eigenvector. So let me write take an, very good. So this is now very straightforward here. from now, okay, take an unit eigen vector for lambda 1 of lambda n of gs, so for the smallest eigenvalue of the sign. Okay, so I'm going to suppose this is called x. Okay, now if you see that what will be this quantity lambda n of ls will be nothing but x transpose ls xs, right? So this is very now this will be, we can actually write this as what? We can write this as the summation over all edges, then xi minus sigma, this is sign. Okay, so let me write it, minus sigma I comma j times xj square. This we have seen. Okay, now what? Okay, now what? If you see that and suppose if you assume that, suppose if you assume that ls is 0, right? Suppose if we assume that, if we assume that suppose this lambda n of ls is if 0, basically if you assume that, okay, this is singular matrix, we will try to reach to some contradiction. In that case, what will happen? If you see, in that case, from there, that means xi, okay, is always equal to sigma I comma j and then this, right? Because every term will be here 0, every term here will be 0. And by the way, whenever the edges are with negative edges, so if I and j are actually with negative, so this is nothing but xi equal to minus xj, and if I and j are with plus, right, so this is xi equal to, maybe I can write xi equal to plus xj. Okay, now since graph is connected, there is a path between any two vertices. This implies that xi equal to xj. Okay, so mod xi equal to mod for all I comma j, for all I comma j, right? Now what is the issue? What will be the issue? Okay, now consider this cycle, the cycle we have taken. Suppose this odd length cycle, suppose if you take this cycle, this one, okay, not odd length, basically a cycle which have odd number of negative edges. Suppose this is a cycle, such a cycle. What will be the problem here? What will be the problem? The problem will be this. Okay, so if you see that x1 will equal to minus x2, okay, then minus x2 is again minus x3, which in fact will become this, but x3 will, and now this is plus, x3 will be equal to, so sorry, there are odd number of negative edges, so let me, so this is actually odd number of negative edges. Okay, so suppose this is the case. Okay, now x3 will be again minus x1, right? Now this tells what? X1 equal to minus x1. This means what? This means x1 equal to 0, but due to this everything is 0, which is a contradiction, because x is an eigenvector, right? It cannot be 0. It cannot be 0. Okay, so that's why our assumption is wrong. That lambda n is equal to 0. By this argument or by this equation, if you see that, okay, lambda n cannot be 0, hence the matrix ls must be non-singular, hence ls must be non-singular. Okay, by the way, this quantity will be always greater or equal to 0, right? Very good. Okay, great. So yeah, so must be non-singular. Great. I hope you enjoyed this proof. Very so this is a nice characterization in terms of the Laplacian matrix, right? In terms of the Laplacian matrix, just check whether it is singular or non-singular. Okay, now let us move to the next result. Okay, but this result is on something called frustration number or frustration index of a signed graph. Okay, so let us see what these two numbers are. Frustration number and frustration index. Okay, frustration. Okay, I think this is spelling is wrong. Frustration. Okay, very good. Okay, so what are these numbers? Okay, so let me first write what we mean by frustration number. Frustration number. Okay, so let GS be a signed graph. Let GS be a signed graph. Okay, the number of edges, whether it's positive or negative, the number of edges, in fact the minimum number of edges whose removal results in a balanced signed graph, okay, that number, the minimum is called the frustration index, the frustration index. Okay, and we will denote it by epsilon of GS. Okay, epsilon of GS. And similarly frustration index or frustration number, I would say. Okay, so this is frustration number and this is frustration index. I'm making mistake in the spelling again. Frustration index. Okay, frustration index is, okay, it's the same definition, same parallel definition. Now instead of vertices, so instead of edges, you remove vertices. Removal of vertices such that the resulting graph is balanced signed graph. Okay, and we will denote it with by this V of GS. And by the way, this, if you check that, this quantity will always be greater or equal to BS. Why it is so? Because just by removing a vertex, right, you can actually remove many edges. Okay, so you just see, maybe you can consider it as again a DIY. Very good. Okay, now let us see a very interesting result. An interesting result is this. Okay, theorem. The result is this: for any signed graph GS, okay, for any signed graph GS, okay, this frustration index is always greater or equals to the smallest eigenvalue of so Laplacian matrix. Okay, how to prove this? How to prove this beautiful claim? Okay, so very good. Yeah, so proof. Okay, how to prove this? Okay, yeah, okay, so let us go ahead with the proof. Okay, so let F be the set of edges whose removal from GS results in a balanced signed graph. Okay, so by the way, so let me denote this. Let the resulting graph be denoted by, let the resulting graph be this GS minus F. Okay, even though this F is set of edges, so just notice that this is the resulting graph after we remove F from the set of edges, so that the graph becomes balanced. So basically, this G minus F is balanced. Okay, G minus F is balanced. Okay, by the way, if it is a balance, then of course there are two partitions, right? Our theorem, so of course there are two partitions. Suppose this is V1 and V2, everything here is plus, and everything is minus. So this is GS minus F. Okay, now the interesting thing is this: F actually with this setup, okay, if you see carefully, F is nothing but the number of edges which were the number of negative which were edges which were in V1 or V2. Okay, those we have actually now removed, right? So these were nothing but number of edges which were in V1 which were negative, again the number of edges which were in V2 which were negative, and also which were the number of edges which were positive in between, right? So union the number of positive edges between V1 and union V2. Okay, so and now not union, actually I would say this between V1 and V2, right? Between V1 and V2. Okay, very good. Okay, so now using this, how can we claim that? This number of edges, basically mod f, is always greater or equal to the smallest Laplacian, the smallest eigenvalue of the Laplacian matrix of signed graph. Okay, so let us actually proceed with, let us cook one vector. Okay, so suppose x is some vector of size n is number of vertices in our graph. Okay, such that xi equals to 1 if I belongs to V1, otherwise 0. Otherwise suppose xi is equal to -1. Okay, now if in this setup, if you see this, by the way, we already know that this lambda n of your signed graph is always due to Rayleigh quotient is always less or equal to this, right? X transpose ls and divided by x transpose x, right? This is divided by this. Okay, so this is nothing but, so x transpose x is nothing but here n, right? So this is nothing but x transpose ls x divided by n. So let me actually further write and let us open it. So this is nothing but xi minus sigma I comma j, right? We have seen it, and times xj square divided by n. Okay, let us inquire about this, and this is overall ij. Okay, now if you see that if this ij is in V1, suppose ij is positive, okay, and it is in V1 and suppose it belongs to V1 or V2, okay, or V2, this quantity will be what? This quantity will become 0, right? Because these are with positive, so and we will cancel it out. Okay, also, so this will, then this quantity will become 0. So numerator contribution, let me say contribution is 0. Okay, similarly if I and j is an edge, okay, and what, so suppose there is a negative edge between V1 and V2. Okay, so this is between this V1 comma V2. Okay, so we're going from, so one end is, so basically this, let me actually write it more carefully here. Suppose I belongs to suppose here this I belongs to V1, and so I belongs to V1 and j belongs to V2, and there is a negative sign. Then also numerator is 0, because in this case what will happen? This is the sign will be the negative, right? The sign of this will be negative, but this is already negative edge, right? So okay, in this case what will happen? Xi will be 1, xj will be what? A -1, right? And then there is also a minus before this, right? So overall this summation will be 0, right? So all this is remaining is nothing but, so all this remaining is, sorry about this, okay, yeah, it is nothing but I comma j belongs to f. Okay, so those are belongs to basically in this set, right? In this set, okay, so and this quantity is for this is nothing but 2, right? So this is nothing but 2 square, because this will be 1 plus 1, so 2 square divided by n. So this is nothing but, so what is this, by the way, the summation? This is 4 times the number of edges in mod, right? The number of edges in mod is this, right? Gs divided by n. Okay, now let us consider that n is greater or equal to 4. Okay, if n is greater or equal to 4, this quantity is again what? If you see here, okay, so this quantity we can write that always greater than this, right? Epsilon times, if n is greater than 4, right? So epsilon of basically the frustration index of frustration number of the sine graph. Very good. Okay, and by the way, so this is proven for, this result is proven for n greater or equal to 4. But what about n less or equal to 3? What about n less or equal to 3? If you see carefully, in this case, either, okay, so the graph is on 3 nodes, at most 3 nodes, so either there will be one negative edge or 3 negative edges. In all the cases, the Laplacian is just to check that the smallest eigenvalue of the Laplacian matrix is actually coming out to be 1, and this is actually the same as the frustration number of this. Okay, so for this also we have proven. Okay, so we have now proven this very beautiful result. So this is actually, just check that this is DIY for you. Very good. Okay, so now let us move to another variety of sine graphs, those we call weakly sine graphs. Okay, weakly balanced sine graph, rather weakly balanced signed graphs. Okay, signed graphs. Okay, so by the way, till now we have seen balanced sine graph, unbalanced sine graph. So what were balanced sine graph? So balanced sine graph was like this. Okay, so there was positive edges here, positive, everything was positive. Okay, so suppose this one, and then this was the case, right? There were two partitions, V1 and V2. Okay, so this is called balanced sine graph, otherwise unbalanced sine. There was very nice characterization in terms of the eigenvalues, right? And also this is possible if and only if every cycle has even number of negative edges, right? Okay, now let us come to this another scenario where not only there are two partitions, maybe there are many partitions. Okay, so everything here is plus, so all these edges are plus, right? So let me actually draw a few more edges. Okay, so few more edges here, so everything is plus, but between any two these clusters or groups, whatever you say, right, subsets, right, these are negatives, okay. Such a possibility, if for a sine graph, if this is possible, for a sine graph, if the following is possible, okay, then we call it weakly balanced signed graph. Okay, weakly balanced signed graph, and in this setup we call it strongly balanced signed graph now. Okay, so this is now strongly, when there are only two clusters. Okay, strongly signed graph. Okay, very good. But by the way, like strongly signed graph, is there a characterization using the eigenvalues? Okay, this is again a challenging question, but in terms of the structure, in terms of the number of edges, number of negative edges in your cycles, we can have a characterization. Okay, so let me write this characterization, and it is, think about it, why it is true. Okay, so GS is a weakly balanced signed graph. This is again a very beautiful if and only if it does not have any cycle with exactly one negative edge. Okay, think about this, why this is true, and also think about some spectral characterization of weakly balanced sine graph. Okay, so I am stopping this lecture here. So this was all about the sine graphs. Okay, and see you in the next lecture. Thank you very much.